So for projectile motion, you're just taking some object and throwing it in the presence of gravity. Generally, we're assuming that gravity is the only force acting on it after you let go. So you got some object, you're throwing it, you're giving it some initial velocity. And of course, that initial velocity, maybe you throw it diagonally, can have an x component and a y component. VIX and VIY. And once it leaves your hand, gravity is the only force acting on it. And what do we know about gravity?
It's only in the y direction.
Yeah, gravity is only in the y direction. And since it's downward, I'll call that the negative y direction. And what do we know about specifically the acceleration of gravity? No matter what the object is, as long as we're on or near the surface of Earth, what's the acceleration of gravity going to be? What is the usual value we use for acceleration of gravity?
10 meters per second squared.
Yeah, acceleration of gravity is 10 meters per second squared. So we'll usually call that g. And the acceleration of gravity is going to be g in the negative y direction and 0 in the x direction. So acceleration of gravity has a y component, specifically negative 10 meters per second squared, but it has no x component at all. Gravity isn't pulling sideways at all. So if the only force acting on the object is gravity, then it has an acceleration in the y direction, negative 10 meters per second squared, and has no acceleration in the x direction. So the x component of acceleration is 0. The y component of acceleration is negative 10. Or we might just write that as negative g and fill in the value later. But that means the acceleration is constant. If this object is in free fall, as soon as you let go, from the moment you let go to the moment it hits the ground sometime later, the acceleration in the x direction and the acceleration in the y direction are constants. And what equations can we always use if the acceleration is constant? What were those equations we saw last time?
Is it like the xf equals x naught plus v naught?
Yes.
It was
The
like
kinematic equations, these always work as long as the acceleration is constant. In general, if acceleration is constant, the kinematic equations can always be used. Because we got those equations by assuming acceleration is constant in the first place. If the acceleration is constant, we can calculate velocity by, how do we generally calculate velocity? If you know the acceleration, what do you have to do to it to get velocity?
Take the integral?
Yeah, velocity is the integral of acceleration because acceleration is the derivative of velocity. Acceleration is a constant. Integral of a constant should just be that constant times t, plus some other constant because it's an indefinite integral. And that constant turns out to just be the initial velocity. Because if you plug in 0 for t, you just get that constant plus 0 equals the velocity at time 0. So velocity equals acceleration times time plus the initial velocity. And we usually write that either as v final or as v of t, because it's just the velocity at any time. So function notation, velocity is a function of time. So that's one of the equations we can always use as long as the acceleration is constant. And we can also take this a step further and get a formula for position. Because if you know velocity, how do you calculate position?
Take the integral of the velocity function.
Right, you integrate again because velocity itself is the derivative of position. So position is going to be the integral of velocity. And I'm going to write position as x for now, but keep in mind this could be x or y. In fact, it might be better to write this as r. We often write, when we're talking about position as a vector, we usually write it as r because it's talking about a distance outwards from the origin. So if you've got some coordinate system and you want to describe the location of this point, the position vector from the origin to that location is a radius. It's from the origin outwards to that point. So we usually call position r if we're talking about position as a vector. So r in this case just represents position, where the object is. Position is the integral of velocity. And we now know that velocity is this linear function, at plus v naught. Integrate that, at becomes 1/2 at squared from changing t to the 1 to t to the 2 divided by 2, the new exponent. Plus, then the constant just becomes that constant times t. And again, since it's an indefinite integral, we need another plus a constant. And what does that other plus a constant represent?
Like R naught?
Yeah, r naught, the initial position. So this is another equation we can use whenever we know the acceleration is constant. That's the position as a function of time. And sometimes this is written as final position, but it's really just the position at any instant in time. So the position at any time is half the acceleration times time squared, plus your starting speed times time, plus your starting position. Or to put it another way, this is where you are at the beginning, plus how far you travel because of your starting speed, plus how far extra you travel because you're accelerating. And that tells you your final position. Any questions on those equations so far? So to apply these, which we can, we are allowed to apply these here because the acceleration is constant. But to apply these, we want to be able to split this into x motion and y motion. Because this object, if you throw it, is moving in the x direction and the y direction. We can treat those separately. We can write out kinematic equations for just the x direction and separately kinematic equations for just the y direction. So if we do that, for velocity, we can certainly split this up into just the x direction and just the y direction. So Vx of t equals, and this, both of these, the acceleration and the initial velocity can have x components and y components. So x component of acceleration times time plus x component of starting velocity. And we can separately write out the equation for the y direction. Same equation, but in the y direction. Y acceleration times time plus starting y velocity. And likewise, the position equation, we can split up into x component and y component. Looking at just the x component, and for this one, we usually wouldn't bother calling it r sub x. We would just call it x. The x component of position, like how far in the x direction, how far horizontally, is 1/2 times the acceleration in the x direction times time squared plus the initial velocity in the x direction times time plus the initial x position. And likewise, we can do the same for y. Y of t is the y component of acceleration over 2 times time squared plus just the y component of speed of initial speed times time plus the starting height, like how far above the ground you start at. So we really have four equations here. We've got two equations for speed in the x direction and y direction, and two equations for position in the x direction and y direction. Any questions on those so far? We can also fill in some of these values. For instance, we know the accelerations. We know acceleration in the x direction is just 0. So if we fill that in, x direction acceleration is 0. And what do we know about the acceleration in the y direction?
It's -10.
Right. And for now, I'm going to write that as -g. That gives us some flexibility in case we're talking about a different planet where g is different. But for Earth, that will be -9.8 or rounded off to -10 meters per second squared. Also, we can figure out more information about v0x and v0y. If we know the initial velocity, presumably we know how fast it's going, and we know what angle it's at. Maybe you know what angle you launch the object at and how fast you throw it. In that case, how would you write out the x component and the y component in terms of initial speed and initial angle?
We would use like sine and cosine, right?
Yeah, sine and cosine would work fine here. And for, let's say for the x component, that's adjacent. So what would we use?
Cosine.
Yeah, so v0x is just going to be the initial speed times cosine of the angle. So however fast you throw it times cosine of the angle you launch it at, that's the x component. Y component is opposite to the angle, so we would use sine, v0 times sine theta. So we can actually make those substitutions in v0x and v0y. That leaves us with vx of t equals 0 plus v0 cosine theta. And note that that doesn't change. Vx of t equals a constant. There's no acceleration in the x direction, so the velocities component in the x direction does not change. For the y component, we've got negative gt plus v0y, which was v0 sine theta. And that does change as time passes. You start with some y velocity, some speed in the y direction, presumably upwards, but you could throw it downwards instead. But this negative gt means the velocity in the y direction, the y component of velocity gets more and more negative as time passes because gravity is pulling it downwards. So that gives us a complete description of how the speed in the x direction changes as time passes and how the speed in the y direction changes as time passes. Any questions on that so far? And a useful way to think of these components, by the way, x component is just how fast it's moving forward without any care at all of how high or low it is. So I usually think of this as the speed of the shadow of the ball along the ground. Like if you throw this ball through the air and you've got sunlight coming from directly above, the sunlight casts a shadow of the ball on the ground directly underneath. So as the ball moves, its shadow is just moving forward along the ground. This is talking about how fast the shadow is moving forward. Or alternatively, let's say you've got a wall behind the ball and you've got a bright spotlight shining to cast a shadow on the wall. That shadow is just going to move up and then back down. Vy is talking about how fast is the shadow on the wall moving. We can also simplify these x and y, the position equations. For x, we've got 0t squared, so we can ignore that term. v0xt, and we already know v0x is v0 cosine theta. So V0 times cosine theta times time plus, and then x naught is just the position that you start at, the position you throw the ball from. And note that this is a linear function. We just have a constant plus a constant times time. So if you graph that time versus x, you're going to get a straight line. The y function, though, if we fill this in, we know the acceleration in the y direction is negative g. So negative g over 2 times time squared. V0y is V0 sine theta, the starting speed times sine of the angle it was launched at, times time. And then y naught is just the height that you throw it from. And what would that look like if you graphed it? If we've got y equals something times t squared plus something times t plus something, what sort of function is that?
Parabola?
Yeah, this is a quadratic function, so its graph will be a parabola. So the position function, or the horizontal position, if you graph horizontal position versus time, you just get a straight line because it's moving forward at a constant speed. If you graph vertical position versus time, you get a parabola because it's going up. Well, presumably if you throw it upwards, it's going to be going upwards, get slower and slower, come to a stop, fall back down. So time versus velocity in the y direction, or time versus position in the y direction, the height, is going to be a parabola shape. Specifically a concave down parabola because the acceleration is negative. Any questions on that so far? And with these equations, if we know some of the information, we can use these equations to get more information. For instance, if you know how fast you threw an object and what angle it was launched at, and the strength of gravity on your local planet, and how high you were when you launched it, and let's say you want to know how high is it after 3 seconds later. Plug in all those numbers, you can calculate the height after 3 seconds. Or in another direction, let's say you want to know when does it land. You throw the object from a certain height at a certain starting speed at a certain direction, and you want to know when does it land. If you want to know when it lands, when it hits the ground, what's its height? If you throw the ball and it hits all the way to ground level, what's the height at the instant it hits the ground?
0?
Yeah, presumably 0, if we're calling 0 the ground level. So if you want to know when does it hit the ground, you would set height equal to 0, and then you could solve for time to figure out when it hits the ground. And since this is a quadratic, that would presumably involve using the quadratic formula to find that time. Once you know the time, though, you could also plug that into other equations. Like, let's say you want to know how far forward it hits the ground. How far does it go along the ground before it hits? If you can solve for what time it hits the ground, you could plug that into this equation to figure out where it hits the ground, like how far forward. And also plug that time into these equations to figure out how fast it's going when it hits the ground. Even you could even find the speed and direction when it hits the ground, if you want to know how fast it's going when it hits the ground and at what angle, by combining those back into magnitude and direction of the vector. Any other questions on that so far? Projectile motion and it hits the wall. What do you mean by hitting a wall?
Sorry, what?
You said projectile motion of a ball and it hits the wall. What do you mean by hitting the wall?
Yeah, so like if there's a ball that is being, like, I guess, shot out of a cannon,
Mm-hmm.
and it hits a wall, like, so it doesn't like complete the full projectile motion like we usually see.
Mm-hmm.
I'm not sure like how to approach that sort of scenario if that comes up?
Well, what sort of information would you be trying to find there? Like where it hits the wall, or how fast it's going when it hits the wall, or what?
I'm not sure. I forgot what the original question was saying, but I can check.
Well, if you wanted to figure out something like where it hits the wall, like how high up or down.
Yeah, I think that was what it was asking.
Okay, if we know something like how far away the wall is from the cannon, in terms of just horizontal distance, we could use this equation describing horizontal position. Let's say we know that if the wall is, let's say, 100 meters from the cannon, you could say the wall is at 100 meters, the cannon's at 0 meters, and if you know the initial speed and angle of launch, you could then solve for time, figure out what time the ball hits the wall.
Oh, so you use the x components first, and then you use the time to solve for y?
Yeah, in that case, you would start with the x components because you know how far forward you want the ball to go before something happens to it. Whereas if you wanted to know something like when does it hit the ground, that's a requirement on the y component. Hitting the ground means y equals 0, or y equals whatever we're calling ground level.
And then like if it like hits the wall and then it like starts to slide down, how do we be able to know how long it takes for it to slide down then? Is that just like a different, is that like not kinematics?
I think it would be. I mean, if we're assuming we're ignoring friction, it's just like hits the wall, stops moving forward, but continues moving downwards.
Yeah, I think so, yeah.
In that case, I think the wall would cause its x velocity to come to a complete stop. So this would be gone, but it doesn't make it stop moving downwards. So I think you could treat it as the y velocity, the y equations just keep going exactly as they did before with no further change. We just stop going forward.
Oh, so you can't use the x anymore, but you use the y instead.
Right. From that point, from the impact onwards, x is just going to be a constant and vx is going to be 0. But I assume the y equations are not going to be influenced by that at all, because when the ball hits the wall is exerting a normal force in the negative x direction. But it's not. I presume it's not exerting any force in the y direction at all, unless there's friction involved.
There's like a friction force. Would that be opposing the y?
Yeah, the friction force, because if the wall is vertical, normal force is going to be straight outwards, perpendicular to the wall. So the normal force is going to be in the x direction. The friction force is going to be in the y direction, because the friction force is always along the surface. The normal force is perpendicular to the surface.
So it would be opposing whatever force it is to go down. So the acceleration?
Yeah. So the friction force between the wall and the cannonball is going to cause acceleration or change the acceleration in the y direction.
Okay.
Any other questions on that? And so from that point onwards, from the impact onwards, I would assume that you would treat it as like whatever y velocity it had at the instant it hit the wall, you would keep that y velocity. But then from that point onwards, acceleration isn't just gravity. Acceleration is gravity and friction force combined. And presumably, if it's moving downwards, the friction force is going to be upwards because the friction force is going to oppose the motion. So the friction force would be partially canceling out gravity. You'd end up with a weaker downwards acceleration.
Okay, got it.
Any other questions on that? So this is just one specific example of the kinematic equations. The kinematic equations can be used in any situation where the acceleration is constant. Even if the acceleration changes at some instant in time, if you can split up the timeline into an interval when the acceleration is constant, and then an interval when the acceleration is a different constant, you can still apply the kinematic equations to each one of those intervals separately. For instance, in that case, the ball hitting the wall changes the situation, but in the entire time before it hits the wall, the acceleration is constant, and the entire time after it hits the wall, the acceleration is another constant. So you can apply the kinematic equations separately before versus after. And in this specific situation of an object in free fall, the only force being gravity, these are what the kinematic equations become just by plugging in the appropriate values for acceleration. And this has tremendous amounts of application anytime you've got an object in free fall, no matter what you know versus what you're trying to find. Like maybe you know how fast it was thrown and you want to know maybe how high does it go. If you want to know how high it goes, what should you assume is the velocity in the y direction when it reaches the highest point it can get to?
Would it like be final be 0?
Yeah, when it's at its highest point, it stops moving up and is about to start moving down. So if you want to know when does it reach its highest point, you would just set Vy equal to 0 and solve for time. That tells you what time it reaches its highest point. And of course, it's still moving forward. So its total velocity is not 0. It's just its y component of velocity is 0. It's still moving in the x direction at the same as the original speed. But set Vy equal to 0, solve for time. That tells you what time it reaches its highest point. And then you could plug that time into both of these equations to figure out how high it is at that highest point, and also how far forward it is, like what point on the ground it's directly over at its highest point. So there's many different pieces of information you could figure out from these equations, depending on what you know and what you're trying to find out. But in general, anytime you're dealing with an object in free fall or any object that's experiencing constant acceleration, I find it's a good start is to write out everything you know, write out what you're trying to find with variables assigned to it, write out any kinematic equations you think might tie those values together, and then look for ways you can plug in what you know and solve for what you don't know. As long as you can get one equation with one unknown, or more generally, a system of several equations with several unknowns, as long as you have the same number of equations as you have unknowns, that's a system that you can solve. Any other questions on that? All right, then let's take a look at the rotational momentum stuff that was mentioned earlier as well. Just a quick example. Let's say you have let's say a solid ball, a solid globe with mass 50 kilograms and radius 2 meters. And let's say it's currently spinning at a speed of, an angular speed of, let's say 3 radians per second. So spinning at 3 radians per second around a vertical axis. And by the way, based on the right-hand rule, which direction would we say the omega, the angular velocity vector is? If it's spinning like this, which direction is the angular velocity?
I'm not sure what you mean by like direction.
Well, angular velocity is a vector. So it's got to have a direction associated with it. This object isn't just spinning at 3 radians per second. It's spinning at 3 radians per second in this sort of direction. So we can associate a specific straight line direction with that using the right-hand rule. If you curl your fingers of your right hand in the direction it's spinning, so curl your fingers this way, because it's spinning in this direction, your thumb is now pointing upwards. So this sort of spin would be treated as an upwards angular velocity. Yeah, that's upwards. So we'd say angular velocity is 3 radians per second upwards. And of course, that doesn't mean anything is moving upwards. Upwards is just the axis it's rotating around. This is rotating around a vertical axis. And of course, a vertical axis could mean upwards or downwards, but if it's rotating in this way, we treat that as upwards. Downwards would be if it's rotating in this way. So this direction of rotation would be considered downwards. This direction of rotation would be considered upwards. Any questions on that so far? And let's say we have a small robot on this. A robot whose mass is, let's say, 5 kilograms. So the robot is just at the north pole of the globe, so to speak, which means it's just spinning in place. The robot isn't really moving around. The robot is just spinning in place at the North Pole. But let's say the robot walks along the globe, along the surface, to the equator. So the final situation is going to be the robot is now standing on the equator as the globe continues to spin around. And we want to know, what's the final angular velocity? How fast is the globe now spinning? First of all, why would you expect the speed to change in the first place? Why would the robot crawling to the equator cause the globe to change its angular speed? Should we expect the total angular momentum to be conserved in this situation?
No, I'm not sure. Is the robot rotating?
Well, the robot is clinging to the surface. So as the globe rotates, the robot is rotating at the same rate. Like if the globe completes one full revolution, the robot has also completed one full revolution.
Oh, so there wouldn't be any external force?
Yeah, or specifically, I would say no external torque. Because if we're talking about rotation, force doesn't matter, but torque does. And these objects are presumably only interacting with each other. As they rotate, or as the robot crawls around on the surface, the globe and the robot are exerting torques on each other, but there's no torques from anything else. No external torques means no change to the total angular momentum. So we can assume that the angular momentum is conserved. The total angular momentum initial equals the total angular momentum final. And how do we define angular momentum in the first place? What is angular momentum?
Inertia times angular velocity.
Yeah, moment of inertia times angular velocity. The thing is, moment of inertia isn't just about mass, because the mass of the system definitely isn't changing. We start with 55 kilograms, we end with 55 kilograms. But moment of inertia isn't only about mass, it's about mass and also what else?
The radius.
Right, the radius, how far that mass is from the center of rotation. And note that the globe itself isn't really changing, but the robot is changing from at the center of rotation, at the axle, to further from the axle. So if the robot has moved further from the axle, if some of the mass has moved further outwards, what happens to the moment of inertia?
Does it increase?
Yeah, moment of inertia depends on mass and how far you are from the radius. If you're taking some of the mass and moving it further from the radius, or sorry, moving it further from the axle, the pivot point, you're increasing the moment of inertia. So if the moment of inertia has increased, what else has to happen to balance that out?
The angular velocity has to decrease.
Right, angular velocity has to decrease so that the total angular momentum is conserved. So omega final is going to be slower in the end than in the beginning. It's still going to be rotating in the same direction. That's not going to change because there's no torques causing it to shift its direction of rotation, but it's going to rotate more slowly. This is exactly the same effect as if you're spinning around with your arms tucked in and you stretch your arms out, that's going to slow down your rotation. You're moving some of your mass out to a further radius. Larger radius means larger moment of inertia, which, if everything else is conserved, means slower rotation. So we should expect the globe to slow down its rotation as the robot moves from the North Pole to the equator. And we can use conservation of angular momentum to figure out exactly how much slower. If we flesh this out with both objects, if we say initial angular momentum of the globe, initial angular momentum of the robot, final angular momentum of the globe, final angular momentum of the robot. And formally, we should be treating these as vectors, but since everything's just in the up and down direction, we can treat these as just the magnitude anyway, since everything only has a z component. So for the globe, for each one of these, we'd be writing out moment of inertia. Although actually, since these are spinning together, they've got the same angular speed. Since they have the same initial angular speed, what can we do with that omega initial in the equation?
We can factor it out.
Yeah, let's go ahead and factor out omega initial. So we've just got moment of inertia of the globe plus moment of inertia of the robot times initial angular speed. And likewise, at the end, they're also rotating at the same rate. So we can factor out omega final and just get moment of inertia for the globe plus moment of inertia for the robot times omega final. The globe is staying the same shape, so IG is just a constant value. But since the robot is moving, we should really mark these as the initial moment of inertia of the robot and the final moment of inertia of the robot, because that does change. And we know omega initial is 3 radians per second. We're trying to find omega final. So how would you isolate omega final here?
Divide by inertia of the globe plus inertia of the robot final.
Yeah, if we just divide both sides by that whole thing, we get this constant divided by this constant, total moment of inertia, times that initial angular speed, 3 radians per second. So the final angular speed of the whole system is going to be this ratio, initial total moment of inertia divided by final total moment of inertia, times the initial angular speed, which we already know. So if we can fill in all of these moments of inertia, we can figure out how the angular speed changes. For a globe, we should be able to just look up a formula for that. It's going to be some fraction of mass times radius squared. I forget exactly which fraction, but we can look that up. For the robot is just a single point mass. The robot is small compared to the other distances involved. So what formula could be used for just a single small object, moment of inertia? How do you usually calculate moment of inertia for just one small object?
Is it like m times r squared or something like that?
Yeah, that should work. And the mass is going to be 5 kilograms. The radius is changing though. At the beginning, how far is the robot from the radius, from the axle?
0?
Right. If you're at the North Pole, you are on the axis of rotation. So that means R is 0. So you get 5 kilograms times 0 meters squared. At the beginning, the robot's moment of inertia is 0. In the final situation, though, how far is the robot from the axle?
It's 2 meters.
Yeah, that's just the radius of the globe itself, which was given at the beginning as 2 meters. So we've got 5 kilograms times 2 meters from the axis squared. As 5 times 2 squared, 5 times 4 would be 20 kilogram meters squared. So we can now say at least that the initial robot moment of inertia is 0, final is 20. And now we just need to figure out moment of inertia for the globe itself. And for that, we should be able to look on a data table, which I happen to have here. We've got a couple of different formulas for a sphere, one of them for a solid sphere and one of them for a hollow sphere. So for the solid sphere, we're going to use this formula. Looks like 2/5 mr squared. So 2/5 times the mass, 50, times the radius squared. So 2/5 of 50 would be 20, times 40 would be 800 kilogram meters squared. So that would be the moment of inertia of the globe, both before and after, because the globe itself isn't really changing. So this tells us that the final angular speed is 800 plus 0 over 800 plus 20 times the initial angular speed. 800 over 820 reduces to 40 over 41, I think. Initial angular speed was 3 radians per second. So 40 times 3 over 41 would be 120 over 41 radians per second. So that is a little bit less than 3. It has slowed down very slightly. But it hasn't slowed down very much because the robot moving out to the edge doesn't increase the moment of inertia a large amount. It only increases the moment of inertia by a little bit. But that is an increase in moment of inertia, so the system does slow down its rotation. Any questions on that?
How did you get 800?
The 800 was from multiplying out the moment of inertia for the globe. For any solid sphere, moment of inertia should be 2/5 times mass times radius squared. Moment of inertia formulas are usually some fraction times mass times radius squared, the exact fraction depending on the shape and how the mass is distributed. For a uniform solid sphere like this globe, it's going to be 2/5 times mass times radius squared. And that you'd usually look up on a data table. We plug mass. Yeah, what was that?
Wouldn't it be 80 though? Because if you're doing 20 times 4?
Oh, that's right. I was thinking 4D somehow. Sorry about that. Thank you. So yeah, if you make that 80 instead of 800. So actually this does make a more significant difference. If we've got 80 divided by 80 plus 20, so 80 over 100, that's not 40 over 41, that's 4/5. So 4/5 of 3 is going to be slowing down more than I thought. That's going to be 12/5 or 2.4 radians per second. So yeah, this slows down from 3 radians per second to 2.4 radians per second as the robot crawls from the North Pole to the equator. Because of the increase in moment of inertia correlates to a decrease in angular speed. Any other questions on that? All right, then I will see you later.
Thank you.
You're welcome.